Swayam Prabha. Digital India. Educated India.
Welcome to this NPTEL course on Muffler Acoustics. So, we are in the week 11 of this course, and for the first time in this course, although quite late, we will be introducing the 3-dimensional analytical solution of muffler systems. So, we will begin with your rectangular chambers, but and different ways how to characterize such a chamber. There are different ways like solving a homogeneous set of equations subjected to inhomogeneous boundary conditions, or the other way around, where we characterize the system by solving inhomogeneous system equations subjected to homogeneous boundary conditions by means of Green's function, and then using it further to derive the uniform piston driven model approximation. So, there are number of things, number of ways in which we will analyze these things, but before we do that, the way we are going to characterize this system is using your impedance matrix things, which is basically nothing but the transfer function. So, let us say you have a it's an arbitrary muffler, and you have say the first port 1, 2, 3, 4, 5 and say 6. Okay. Let us say we have 6 ports. It could be actually, instead of calling it like 5 or 6, I would say that n minus 1 nth port. So, how do you characterize such a system? So, if we recall our discussions that we had in the I guess week 9 later parts, or week 10 I guess the initial parts, you will see that an impedance matrix is the best way to characterize such a system. So, I am dropping the tildes, excuse me for that. So, here you have this kind of a thing, so we get this is such a matrix. So, what is that matrix called? Where we relate pressure to the acoustic mass velocities at the different ports. Such a matrix is called an impedance matrix. So, how do you write this? So, it is basically Z11, Z12, Z1n, Z21, Z22, Z2n, Z31, Z32, like this, Zn1, Znn and Z3n. So, this is the n cross n system. So, how do you get the different parameters for that? Let us go back to our schematic or the line diagram. So, what we do, let's say we excite the system by means of some kind of a piston excitation somewhere here, to and fro motion. We generate waves, we block all the ports here, or you could also block it elsewhere, so that the effect of sudden expansions at these ports might also come into effect. But for argument's sake, let us say we want the characterization right from the interface. So, we will move this piston somewhere here and excite it right at the port chamber interface. Okay. So, when we excite with a uniform velocity or certain velocity and block all the ports, so what do we get? The mass velocities V2, V3, all the things Vn is 0. Under such a thing, what will all these things become? P1 is equal to Z11 times V1, Z12 times V2 and so on. So, let me expand this guy out. P1 is equal to Z11 times V1, Z12 times V2, Z13 times V3 and Z1n times Vn. But then all these things are 0. Why? Because you have blocked all the ports, you have covered with the rigid surface. So, the acoustic velocity normal to the surface is necessarily 0. So, you get P1 by V1 is equal to Z11. You get this kind of a thing. Okay. So, similarly, now if you were to have a mount a sensor here, now put the sensor here P2. So, P2 by V1 will get you Z21, P3 by V1 will get you Z31, because all the other components we can write down this entire equation like this, all these things are 0. So, Pn by V1 is equal to Zn1. So, like this, if we block all the other ports, all the other ports are blocked and only the first excitation only at the first port is there, then this entire thing you will get the first column. Similarly, if you block the second port, excite at the second port and block the ports 1 to 1 and 3 to n, you will get basically the second row, second column, Like this you could traverse the entire thing and characterize the system using n cross n thing. It is very similar, P1 by V1 or P2 by V1, these are very similar to your transfer functions, acoustic transfer function, which lot of authors prefer to call them. In a sense, impedance matrix parameters or acoustic transfer functions are one and the same only. They have been used interchangeably in many papers, but they are one and the same. And using these transfer functions or the impedance matrix parameters, one can also obtain the transfer matrix parameters or the 4 pole parameters. We will see soon, but what we will do in this lecture, because we are going to use the impedance matrix formulation to characterize a rectangular chamber and a circular chamber in this course, and I might just talk about little bit about elliptical mufflers using analytical functions, well, just a glimpse of that, but perhaps an impedance matrix kind of a thing would be very much suited for analysis of such reactive chamber mufflers. And before we do that, let me sort of more firmly establish this theory, which I am in the process of course, and also talk about how do you obtain, finally we need to obtain the transmission loss. So, how do you obtain that, and how do you get different conditions in which transmission loss goes to show the peak or show the trough, much like your transfer matrix T matrix parameter. So we have basically your P is equal to Z V, this is n cross n. So, we would want such a thing here, A1 P1, A2 B2, A3 B3. So, what are these? A1 is the wave that is incident here, B1 is the one that goes here. Similarly, A2 is here, B2 is here, AN goes here, BN goes here. So, basically what we can do, we can write the entire, this column has A1 plus B1, A2 plus B2, A3 plus B3 and AN and BN. Okay. We can do that, and this is your Z11, Z12 and Z1n, and this will become your Zn1 and Znn, and you will get your, and mass velocities, mind you, going back to the definition, A1 minus B1, A2 minus B2 by Y2 and AN minus BN by YN. So, I's are the characteristic impedance of the ports. So, you get this sort of a thing. So, now what we do is basically A1 plus B1, A2 plus B2 and AN and BN is equal to Z times 1 by Y, where Y is also n cross n, and this is also n cross n, and this becomes A1 minus B1, A2 minus B2 and AN minus BN. Okay. So, your Y is the diagonal matrix, I would write this as diagonal n cross n, and so what will happen here is that A1 plus B1, like this you get AN plus BN will be Z11 times, this will become your Z11 times Y1, because you remember, so each of these terms will be multiplied. You can consider this Z11 multiplied by Y11, Y1, I am sorry, Z12 multiplied by Y2, and so on. So, so basically what will happen is that this will become Z13 and Z21 will be multiplied by Y1. So, here you will have Z21, Z22, Y2, Z23, Y3, Z2n times Yn, Zn1 times Y1, Zn2 times Y2, Zn3 times Y3, Znn times Yn. Okay. So, this will become A1 minus B1, A2 minus B2, and this will become An minus Pn. Okay. So, we are in the process of obtaining what is known as a scattering matrix parameter. So, basically scattering matrix, eventually you might be wondering what exactly we are trying to do here. We are trying to relate the reflected wave amplitudes Bi's, that is B1, B2, B3, Bn, in terms of the incident wave amplitudes A1, A1, A2, A3 and so on, An. So, this is now it becomes rather simple. What we now basically do is that rearrange a few terms. So, what we can do from here is that arrange terms like B1, B2, Bn, this can be rearranged as C inverse D, and this is nothing but A1, A2, An. So, what exactly is C and D matrix? So, C matrix is nothing, it does involve a little bit of algebra. So, I would request all of you guys to please do the longhand derivation and practice it by yourself. So, this is nothing but Z11 by Y1 plus 1, Z22 by Y2 plus 1, and this is Zn by Yn plus 1. So, what about the other terms? It is Z12 by Y2, and we get Z1 n by Yn, and Zn1 by Y1, and this is like this. So, like this one can populate the entire thing to get the C matrix. So, last term will be Zn minus 1 and like this, and your D matrix is nothing but you will pretty much get the same thing, but instead of a minus sign, instead of a plus sign, you will have a minus sign. So, everything else will be the same, and here we will have Z22 Y2 minus 1 like this, and this will be your Yn, and this will be your n plus 1 Y1. So, C and D. So, basically we get C inverse D, and this is CD. So, this can be written in a much more compact manner, where your B vector, I would say B vector, or the vector of the reflected wave amplitude. So, let me sort of write it down in the full blown out form itself: B1, B2, B3, Bn is equal to, this is equal to S matrix, but this can be written in the form of Z matrix, and Y, which you should remember, this is a diagonal matrix. So, Y inverse will be y is a diagonal matrix, so it is y1, y2, y3, yn all on the diagonals, everything else is 0. So, y inverse if you do, you just have to take the inverse of the diagonal element. So, this will be plus I. So, this is a much more compact way of writing stuff, and z y inverse minus I times A1, A2, A3, An. So, like this we can keep doing, and there is yet another well, perhaps a little bit more compact way of doing this thing is that if you realize this, that instead of minus I, if you write plus I, then you have to subtract minus 2I. Okay. So, once you multiply this guy with this z y inverse plus I whole inverse with this particular thing, you will get I matrix, and this will be minus 2 times this thing. So, basically this entire thing is called the scattering matrix. So, scattering matrix, one compact way of writing scattering matrix is also given for a n cross n system, will be given by Z matrix, impedance matrix, which is also n cross n matrix. I am not writing it though. Y matrix, y inverse plus I, Z into y inverse plus minus I is equal to I times minus 2 Z y inverse and plus I. Okay. So, you will get this sort of a thing. So, this is your S matrix. Basically, scattering matrix relates the waves that are reflected from the ports to the incident wave. So, now we might be asking why are we doing this. So, we can we can have any sort of, this is a very powerful representation. You would realize the importance of this thing by actually considering n plus m system, where you can have n inputs and m outputs. So, n can be any number, it can, you can actually instead of n you can put it n plus m. So, you can restructure the matrix by putting the first n rows can be your n inlets and m can be outlets. Of course, in in conventionally you would analyze a single inlet and single outlet system, but typically the photographs of lot of commercial vehicles, if you see on the internet, or if you go around and have a look at the muffler photographs, you will see double outlet mufflers as well. So, basically what happens is that the analysis of such a system, B1, B2, B3, where B1 is the inlet port and S2 and 2 and 3 are the outlet ports. So, S11, S12, S13, S21, S31, S33, this will be your scattering matrix for a single inlet and a double outlet system. When you talk about characterizing a system, you can have actually an n inlet and m outlet. So, the first chunk will become inlet ports, reflected waves at the inlet ports, and the other chunk will become reflected waves at the outlet ports, which you which you intend to find out. Now, let us first analyze a single inlet and single outlet system in terms of scattering matrix. Impedance matrix, we will be characterizing a single inlet and multiple outlet, a single inlet and single outlet rectangular chambers or circular chambers in terms of circular functions or Bessel functions, whatever the case may be. But we will also analyze a muffler with 3 ports. So, one of the ports can be an inlet port, the other 2 can be outlet ports, and we can optimally choose the sort of location of such ports to make things quite interesting for us. So, in terms of how do you obtain the broadband transmission loss. So, you have this B1, B2 is equal to S11, S12, S21, S22 times A1, A2. Okay. Now, if you set your let us say you have a system like this, okay, incident wave A1 and so So, here one thing that I kind of forgot to mention, I should have mentioned, apologies for that. Velocities, the direction of velocity is considered positive looking into the system. So, what it means for us, it has a great significance, is that when you consider a system like this, A1 is the incident wave here, and A2 is the incident wave here, and the one that goes, this is B1, this is B2, and direction of mass velocity is considered positive into the system, V1, V2. So, V1 is equal to S11 times A1 and S12 times A2. So, if we set the incident wave to be 0 at the inlet, so we get A2, if we set A2 0, basically no incident disturbance is there on the boundary. So, we get B1 is equal to S11 times A1 and B2 is equal to S21 times A1, because A2 is 0. What it means is that here we are basically by exciting the system, let us say this muffler proper single, this is the inlet port, this is the outlet port. So, we are connecting the inlet to the engine, to the engine exhaust, and this is the tailpipe. So, there are no reflections. If we have an anechoic termination, okay, if we have an anechoic termination, what we will get is that A2 will be 0, there will be no incident wave or very negligible for the frequencies of interest, and there will be only B2 waves that are reflected downstream. Okay. So, B2 which will be of great interest to us, because that will determine the amount of acoustic power carried into the anechoic termination, and A2 is 0 because of anechoic termination, and here you will have non-zero B1 of course. So, exactly these are exactly what you would do when you obtain the transfer matrix, to characterize the system in terms of transfer matrix parameters and find out A1, B1 and all that. But here we are moving towards a very general kind of system. So, B1, so I will get rid of this part and we will just represent B1 reflected wave at the inlet port and reflected wave outlet port in terms of these S11, S21. So, what is the transmission loss then? The transmission loss is defined as 10 times, obviously log to the base 10 of the acoustic power incident to the acoustic power transmitted in an anechoic termination. So, here one thing that is very important, I am saying this thing, repeating this thing again and again, is that A2 must be 0, then only this thing will work, and that means that implies the implication, or that implies the presence of an anechoic termination. So, what is the acoustic power in terms of these things? Let me go to another slide. So, B1 mod B1 square divided by 2 rho naught Y1 is W incident, okay, and mod B2, I am sorry, this is the wave, I am sorry, my mistake, this is the acoustic power that is being carried away back into this direction. So, this is of less importance. The acoustic power that is incident, that is given by this thing, okay. The one that is carried away in the anechoic termination is this thing, Y1 and Y2, they can be different in general. So, 10 times log 10 So, let us do some cancellation, and A1 is obviously we know, B2 we could write it in terms of S21. Okay. And of course, we will have Y2 on the top and Y1 on the denominator. So, transmission loss TL is 10 times log 10 by Y2 by Y1 S21 mod square. Okay. We get that. So, entire thing, remember, we got the same thing in terms of your T matrix parameter. Apologies if I am getting something wrong, it is probably something like Y2 plus T22 Y2 by Y1, something like this, was not it? So, This is the counterpart, and when you establish, when you represent S21, once you use, I leave this as an exercise, you must do that, and we will discuss all the implications of this. Is that when you sort of figure out that this is a scattering matrix for a 2-port system, it looks like this, and then once you find out what S21 is in terms of what S21 is in terms of the impedance matrix parameter, you will realize that the transmission loss can be very nicely expressed in the following form, that TL is equal to 10 times log 10 and 1 by 4 y1 y2. This you can sort of ignore for now, but Z11 times y1, Z22 times y2, Z12 Z21 by Z21 mod square. So, you will get this. So, let us also quickly analyze what does it mean. So, clearly different conditions under which we will get attenuation peaks, conditions under which we get attenuation peaks or trough. Okay. So, when Z11 is going to infinity, Z11 is tending to infinity, and Z22, Z21 and Z12, generally it is seen that Z12 is equal to Z21. Why? Because of acoustic reciprocity. Remember our discussions long time back in, I think, in week 10. So, if you excite the system at one port and measure the response at other port, keep the things aside and do the reverse, you will see the same thing. So, this follows from acoustic reciprocity, that which basically says that if the source and receiver positions are changed, then the response does not change. Well, this is true when you do not have a mean flow in general, okay, but otherwise you will have things Z22, Z21, Z12, all right. Now, all these things are finite and Z11 is going to infinity, then it is easy to see you will get you will see that the log of the argument is going to infinity. So, you must be getting an attenuation peak. Okay. Other condition, of course, Z22 is going to infinity and Z11, Z12, Z21 all are finite. Okay. And what is the other condition that you must have, that where you have your attenuation peak? So, the other condition is that when Z11 and Z22, Z11 and Z22 both are tending to infinity, but Z21 and Z12 are finite. Such a case is a little rare, but it does happen. This can actually happen very frequently by just optimally locating a certain port, so that certain mode is excited by one port, but other port does not excite that particular mode. For example, in a concentric circular duct, if you have a port like this, one port center, one port offset. So, here due to this port, as we can see, only the radial mode or radial modes will be excited apart from the plane wave, circumferential modes will not be excited. And due to this port 2, you will have your all the modes, azimuthal modes, I mean basically your circumferential modes and radial modes all will be excited. So, basically at the cut-on frequencies of the 1 0, 2 0 and n0 mode, Z22 will tend to infinity, Z11 will be finite. But for radial mode special case, if you offset it at certain distance, say that this is on the nodal circle of the 0 1 mode, radial mode, then at 0 1 mode resonance frequency Z22 will be finite, and Z11 will tend to Z11 will tend to infinity. So, you can get an attenuation peak even at the radial, at the resonance frequency of the 0 1 mode by centering the port 2 at the radial at the nodal circle. We will have a look at all these beautiful results when we talk about the 3-dimension analysis. So, that is one thing, and that is one thing. Now, Z11 and Z22 both tending to infinity, Z21 and Z12 remaining finite, that will also give you a peak. Another peak that is obviously evident when Z21 tends to 0 and Z12 will also tend to 0 because of reciprocity. hence, but Z11 and Z22 they are all, they can be finite or they can be infinite regardless of the magnitude. If Z22 tends to infinity, tends to 0, Z21 tends to 0 at a particular frequency, you will still get a attenuation peak. On the one condition for getting a trough is that when all the parameters, Z11 you get troughs number of times. So, Z11, Z22 and Z12, Z21 they are all tending to infinity and they are tending to infinity at the same rate. Then what happens that the numerator of this thing can be very nicely written as Z11, let me go to this thing, Z11, Z22, okay, and Y2, Y1 into Z22. So, these can be neglected because probably not at this stage. So, I will still write it down here, plus Z11, Y2, Z22, Y1 plus Y1, Y2, okay, sorry for that, and minus Z21 minus Z12. So, when under the condition when you have your this term tending to infinity, you can sort of clearly ignore the Y1, Y2 which will be much smaller, okay. And if these things they go to infinity at the same rate, each of the parameters, then Z11, Z22 they are all for a reciprocal and a conservative system they are all purely imaginary. So, when they are all tending to infinity at the same rate, then what will happen is basically this guy can be sort of ignored or probably they cancel out and you get Z11 Y2 and Z1 Z22 Y1 Z21, okay, and this is 1 by 4 times Y1 Y2 log of this. So, basically when Y1 and Y2 they are all same, when Y1 and Y2 they are all same, they are equal, you can sort of take this out and you can probably, since they are all tending to infinity, what will happen is that this can basically be approximately written as 10 times log 10 by Y2 by Y1 and 4, this is square of course. So, 4 Y1 Y2 square. So, then when Y1 and Y2 are the same, then you can clearly show that this is equal to 0. So, basically these are the conditions under which you will get trough in the attenuation graph. Now, there is another thing that I want to talk about is that systems when you have double outlet, you have your B2, the transmission loss is given for such a system as single inlet and double outlet as 10 times log 10 and you have your A1 mod square by 2 rho naught Y1 like this, and then you have B2, you can write this in terms of S1. So, 1 by Y1 and S21 mod square by Y2 and S31 mod square by Y3. So, then you can basically, this is the transmission loss TL1 I will say, because 1 is the inlet. So, by doing these manipulations you can get the transmission loss for making the port 2 as the inlet and ports 1 and 3 as the outlet ports and so on. So, in general you can find out a transmission loss for a single inlet and multiple outlet system by these scattering matrix expression, and trust me, these S matrix parameters get very nasty once you increase the number of ports. So, I would just evaluate them numerically rather than finding out conditions under which you are getting peaks or attenuation troughs and all that. So, with this discussion I will close off the lecture 1 of week 11. When we meet tomorrow for lecture 2 and possibly combined lectures 2 and 3 of week 1, we will analyze a rectangular chamber using different methodologies like homogeneous system equation subject to inhomogeneous boundary conditions or inhomogeneous equation subject to homogeneous boundary condition, that is your Green's function approach or a uniform piston driven approach. One of them we will follow and try to figure out some transmission loss parameters of certain configurations. Lectures 4 and 5 will be on circular chambers, and let us see how far we can progress with these sort of things. There are quite a few things to cover. So, With this, I will end the lecture for today and I will see you tomorrow. Thanks.